Okay, so in Module 3, we're going to take a look at probability and probability calculations. We'll start out here with basics in Module 3a. Probability is important for a whole variety of reasons. It's the basis for doing statistical inference, that is, for making conclusions about overall populations based on samples. For example, if you conduct an opinion poll of whether people did or did not like a movie, or whether people do or do not plan to vote for a certain political candidate, you can only do that with a sample of people, and the poll is usually expressed as a percentage with something called a margin of error, which means that the true population value is expected to fall within that, plus or minus margin of error. We also make statements like some test, such as like a test of a new medication or something, is statistically significant at the 5% level. We'll talk a lot more about what that statement actually means. Statistics and probability calculations are used in things like calculating expected profit in the future, calculating risk of whether you might achieve that profit or less, describing the uncertainty in a certain business process, and so on. Generally speaking, people's intuitions about probabilities are pretty bad. In particular, people are really bad at thinking that very unlikely events are higher probability than they are in reality. Because we see these lurid stories about airline crashes, for example, on the news on a fairly regular basis, a lot of people are very frightened about flying and think that flying is dangerous, when in fact flying is dramatically less risky than driving in a car. But accidents with involving cars are reported, but not not over-reported and not discussed endlessly with graphic pictures of what's going on and so on. Here's an example of a couple of statements that do not mean the same thing, but that might confuse people to think that they are. We have a statement, which let's assume is true, that 90% of individuals who do not make a return visit to a website are first-time visitors. Okay, so that means that if you go to a website and you leave the website and don't return, 98% of those people are first-time visitors. Now, another statement that we could make is 98% of first-time visitors will not make a return visit to a website. That sounds kind of the same, and so a lot of people would be confused into thinking that these are the same statements. But in fact, they're not the same statements at all. Let's suppose that 1,000 people visit a website and then leave the website. 98% of the individuals who do not return were first-time visitors to that website. But that does not in any way mean that 98% of first-time visitors will not return. The percentage of visitors who will not return could be much lower than 98% or higher than 98%. They're not the same statements. Okay, so what we need to do in this section is to introduce some terminology and calculations involving very basic probability and how to interpret the concept of probability. Probability is usually described using set notation. We have these things called events. We talk about an event A or an event B, and we ask things like, what is the probability that both event A and event B will occur? Or what is the probability that event A or event B will occur? Now, when an experiment is performed, or when a trial is performed, or when a sample is taken from a population, some outcome occurs. If you flip a coin, you get a head or a tail on the coin. If you select someone at random and ask them what political party they belong to, they will tell you whether they are a Democrat, a Republican, a Libertarian, a independent, whatever party it is that they might belong to. These are specific outcomes that can occur. An event is actually a set of possible outcomes. So if we, for example, think about the probability of, if we think in terms of rolling a die, a six-sided die that is fairly balanced, and so that there are equal probabilities of each of the six possible sides coming up. So an outcome, when you roll the die, the possible outcomes are that you roll a 1 or a 2 or a 3 or a 4 or a 5 or a 6. Those are the only six possible outcomes. An event is any set of those outcomes. And so we can talk about the probability of some event occurring. An event might be a set containing a single outcome. So it makes sense for us to ask, if I have a fair six-sided die and I roll it, what is the probability that I will get a 2? Well, 2 is one of the six possible outcomes. We claim that the six possible outcomes are equally likely to occur, and so the probability of getting a 2, the probability of that event where we got a 2, is 1 out of 6. But another event that we might describe is, okay, we're going to roll this fair die. What is the probability of getting a value of 3 or less? Now, remember that there are six possible outcomes, 1, 2, 3, 4, 5, or 6. The event that we're interested in here is whether we roll a number that's 3 or less. Of the six outcomes, 3 of those outcomes are contained within that event. So if we roll a 1 or a 2 or a 3, then the event that we have rolled a value of 3 or less has occurred. That's true. But if we roll a 4, 5, or 6, then the event has not occurred. Since there are an equal number of outcomes in in achieving the event versus not achieving the event, we would say that our probability of that event is 0.5. Okay, 3 out of 6. Another possible event that we might have if we roll one fair die is, what is the probability that we will get a value when we roll the die? Well, in this case, we've got the set of all possible outcomes described by this event. And so the probability that we will get some outcome when we roll a die is is 1, all right? 6 out of 6, 6 divided by 6 is a probability of 1 that we do get some side of the dice displayed. Another possible event is if we roll this die, what is the probability that we do not get a value between 1 and 6? Well, this is impossible. There are 0 possible outcomes that don't have any value between 1 and 6. So the probability of that event occurring in this case would be a 0. Okay, and then we can talk about the probability of some event and some other event occurring, the probability of some event or some other event occurring, and we can also talk about the complement. That is, if the probability of some event occurring is a certain value, then the complement is the probability of that event not occurring. All right, onward ho. Let's take a look at some examples and definitions of things. So the probability of some event A is normally written as P parentheses A, and a probability is always some number between 0 and 1. It does not make any sense for a probability to be negative, and it does not make any sense for a probability to be more than absolute. Okay, so probability values always fall between 0 and 1. For some specific examples, if we have a fair coin and we flip the coin and the coin lands on heads, head is one of the 2 possible equally likely outcomes here. And so we would say that the probability of a fair coin landing on heads is 1/2. If we look at a weather report, we might get told that the probability it's going to rain tomorrow is 0.8. Okay? Now, we might not be very confident that this weather report is reliable, but nevertheless, the probability, we are told here that the probability that it's going to rain tomorrow is 0.8, or often this would be expressed as 80%, an 80% chance of rain. If I have a die, then as we described, there are 6 possible outcomes here, and the probability that I might roll a 1 or a 2 or a 3, well, there are 6 possible outcomes. The probability that I might roll a 1 or a 2 or a 3 is going to be 3 of those 6 possible outcomes. So again, the probability of this event is going to be 0.5. The complement of an event is simply the case in which the event does not occur. So if we describe the probability that it's going to rain tomorrow as 0.8 or 80%, then the complement of that is the probability that it will not rain tomorrow, and that has to be 1 minus whatever the probability that it will rain. The notation, the most common notation used to express the complement of some event is tilde of the event. So here, if we're talking about the probability that it's not going to rain, if we know that the probability that it is going to rain is 0.8, then the probability that it is not going to rain has to be 1 minus 0.8, or 0.2, or 20%. Using the example of rolling a die again, we describe the event A, that when we roll the die we get either a 1 or a 2 or a 3. The complement of that event is that we do not get a 1, we do not get a 2, we do not get a 3, so we have to get something that is some other outcome, 4, 5, or 6. And in this case, we said, okay, well, the probability of rolling a 1, 2, or 3 is 0.5. The probability of rolling a 4, 5, or 6, therefore, must be 1 minus 0.5, which is also 0.5. And that, we get the same result whether we think about 4, 5, 6 as the complement of 1, 2, 3 and compute the probability by saying 1 minus 0.5, or we think about this event directly as the event that we roll a 4, 5, or 6, that is also 0.5. So we get a probability for rolling a 4, 5, or 6 of 0.5, either if we calculate the probability directly or if we calculate the probability as the complement of 1 or 2 or 3. Interpreting probability conceptually is a sort of philosophical issue. If I have a fair coin and I flip that fair coin, then we say that the probability of getting ahead is 0.5, and the probability of the complement is 1 minus 0.5, which is also 0.5. That is, we have a 0.5 chance of getting ahead. We also have a 0.5 chance of getting a tail. We claim that this is true, but what does that even really mean? Because when we make this statement about the probabilities, we're making some kind of assumption about the coin that it's equally likely to produce a head or a tail. And we're making some claim about the future, about what's going to happen in the future, even though we haven't flipped the coin yet. So one way of thinking about our claim of probability is that, well, what we mean by that probability is if we flip the coin n times, and as n got larger and larger and larger and larger, then if we counted up the number of times we got heads in this huge number of trials, and we divided by the total number of trials that we ran, by saying that the probability is 0.5, what we're saying is if we did this huge number of trials and divided by if we counted the number of heads we got in n trials and divide by n, that number should approach 0.5. All right, it's never going to be exactly 0.5, and that should be, well, I mean, it might occasionally be 0.5, but any odd number of coin flips that you do cannot produce an equal number of heads and tails. There's always got to be at least one more head or at least one fewer head if we do an odd number of trials. So this thing is a limit being described here. It's not going to be true for every single trial or every single experiment that we perform. Another way of thinking about what we mean when we describe the probability of something is that we're specifying the proportion of some population that satisfies some characteristic. Like, if we say that 27% of people, 27% of adults in Pennsylvania wear glasses, we just claim that this is true. We're not going to produce evidence, but if we claim that this is true, then we would say if we selected an adult in Pennsylvania at random, the probability that that person wears glasses is 0.27 or 27%. All right, so this is just a description of the proportion of people who wear glasses to people who don't wear glasses. We can do the same thing with a coin. The proportion of heads is 0.5 of the possible population of outcomes, either a head or a tail. Okay. Now, the notation A and B, probability of A and B, means that both event A and event B occur. And we read that notation by saying that we're asking for the probability of both A and B occurring. If we think of this circle on the left here as the proportion of situations in the world where A can occur, and the circle B as being the proportion of situations in the world where B can occur, then it's this intersection between those two circles that represents both A and B occurring. So what we're asking with this notation is what is the probability of this intersection occurring? For example, we might have the event that, okay, we're going to select a person at random, and one event might be that the person is male. Okay? So that's going to be slightly less than 0.5 on a global basis. Event B might be the probability that this person is 6 feet or more tall. Okay? And so we perhaps have some kind of proportion of, based on some measurements that we've taken, we might have some proportion of people in the world who are taller than 6 feet. In the intersection here, we have men that are taller than 6 feet. Okay? Now, the union symbol would indicate, all right, what is the probability when we select someone at random that this person is a man or that this person is taller than 6 feet? Okay? Notice that in this case, this intersection is going to be people who are both men and taller than 6 feet, and that's going to complicate our calculation of how to compute this probability of one event or another event occurring. Okay, so the probability that either A or B occurs is going to be the probability that A has occurred. All right, that's just going to be the proportion of human beings that are men, something like 0.5, a little bit less. And then plus the probability of the human that we select being greater than 6 feet tall. Okay, now that's, I don't know what the probability of that is, but let's imagine that it's 0.3. Okay, so if we choose some arbitrary person at random, let's say that there's a 3/10 chance of 0.3 chance, 30% chance that this person is 6 feet or more in height. All right, so if we want to calculate the probability that we randomly select a man, we randomly select someone who is a man or is more than 6 feet tall, this is going to be the proportion of all humans that are men, the proportion of all humans that are 6 feet tall. But notice here that if we just add those two values together, we're double counting this intersection, so we also have to subtract one copy of that intersection. Okay, so the probability that this person is a man plus the probability that this person is 6 feet tall or more minus one copy of the probability that the person is both a man and greater than 6 feet tall. Okay, now we describe two events as being mutually exclusive if it is not possible for them both to occur. Okay, for example, let's suppose that our event A here, again, we're going to select some person at random from planet Earth. What is the probability that that person is married? Okay, well, it's, it is whatever it is. It's, I'm just going to pick a number out of thin air. Let's say it's 0.6, okay? Typically we don't, young children who are a significant amount of the population, in most cultures would not be married. Elderly people or middle-aged people may have lost their spouse or divorced or something. So let's suppose that we have a 0.6 probability that someone is married. Perhaps event B here is that the person that we have randomly selected is not married. Now, the probability that a person is married and not married is 0. These are mutually exclusive events. B is the complement of A and vice versa. All right. As another example, this time involving a fair six-sided die. If we roll the die one time and we ask, all right, what is the probability that we got an even value versus what is the probability that we got a 1? Well, the probability that we got an even value is 0.5 because 2, 4, and 6 are half of the possible outcomes that might occur. The probability that we rolled a 1 is 1 out of 6. Okay? But they are mutually exclusive events. If A occurs, that means that we rolled either a 2 or a 4 or 6. So B cannot have occurred. And vice versa. So A and B are mutually exclusive events in this case. And if two events are mutually exclusive, then the probability of both things occurring is simply the sum of the individual probabilities. Okay, let's think of that in terms of, what is the probability that somebody is married? Well, it is, let's imagine that it's 0.6. The probability that someone is not married, that's a complement. So that has to be 1 minus the probability of A, let's say 0.4. And the probability of someone being married or not being married is going to have to be 1. Every person, unless there's some culture somewhere that I really don't understand. Generally speaking, given any person, that person either is married or is not married, all right? And so in that case, we just add the probability of them being married plus the probability of them not being married to get the probability of both things being, of either of the two things being true. Okay. Now, some tests of understanding here. Let me flip on my document camera. Okay, get this organized here. There we go. We're going to do some illustrations here involving rolling a fair six-sided die, which means that any of the 6 values is equally likely to occur. Since there are 6 possible outcomes, and each outcome is equally likely, then the probability of each individual outcome is 1 out of 6. Okay, there's a 1 out of 6 chance that we'll get a 1, a 1 out of 6 chance that we'll get a 2, etc. What if let's have the event A be that we have rolled an even number, and the event B be that we have rolled a number less than 4. Okay, so A is even number, B is a number less than 4. And we're asked to find the probability. What is the probability of both A and B occurring when we roll our die one time? Okay, well, as I described, there are 6 possible outcomes when we roll a die. The roll of the die might be, okay, so the outcomes are going to be 1, 2, 3, 4. I'm running out of space. 5, 6. Okay, so those are the 6 possible outcomes. And the event A being true means that the outcome that we got is an even value. All right, so there are 3 outcomes that are even, so the probability of that is 3 out of 6 is 0.5. The probability of getting less than 4, well, that would be a 1 or a 2 or a 3. So the probability of that is also 3 out of 6 is 0.5. But what we're asked is, what is the probability of A and B both occurring? Well, in this case, B only consists of these outcomes 1, 2, 3. And within those outcomes 1, 2, 3, the only outcome that is also even is 2. And consequently, the probability of A and B is just 1 possible outcome out of 6 possible outcomes, so it's 1/6. All right? So that's part 1. Now, part 2, what is the probability of either A occurring or B occurring? Well, let's see. We can examine the available outcomes. Actually, I'm sorry. We are now going to use the fact that we just described on the previous slide. Okay. We're going to use the fact that the probability of A occurring or B occurring. Sorry, back one more slide. We're going to use this formula that we described and demonstrated. I won't say proved, but we described it and demonstrated it back here on slide 8. So the probability of either A or B occurring is going to be the probability that A has occurred plus the probability that B has occurred minus the probability that both things have occurred. And we have these numbers. So this is going to be the probability of A plus the probability of B minus the probability of A and B. And we have all these numbers. We know that the probability of A and B is 1/6. We know that the probability of B, we've already figured out that the probability of B is 1/2, let's say 3/6, just to have the denominator the same everywhere. And likewise, the probability of A, the probability that we get an even number, is also 3 out of 6. So the probability that we get either an even number or a number less than 5 is 3 plus 3 minus 1 is 5 out of 6. So this is 5 out of 6. Now, we could have considered the outcomes directly, and we could have discovered the same thing not using our formula, but since since we know this formula, and since we already have computed the probability of A, the probability of B, and the probability of A and B, it's easier to just compute this number as opposed to counting up outcomes. Okay, so outcome 1 is in B. Outcome 2 is in both A and B. Outcome 3 is in B. Outcome 4 is in A. Outcome 5 is not in either event. Okay, so we have 1 that's not in either event, and outcome 6 is in A. So we have 5 events out of 6, 5 out of 6, that are in this event, either A or B occurring. Okay. Next up, we're asked, let me scoot my paper up a little bit here. We're asked, what is the probability, or I'm sorry, if the probability of A is 0.15, then the probability of the complement of A is what? Well, if the probability that A has occurred is 0.15, then the probability that the complement of A is the probability of anything other than A occurring. And I hope it's both intuitively obvious and also, of course, we talked about the formula. I hope it's intuitively obvious that the probability of the complement of A is going to be 1 minus 0.15, which is 0.85. 0.85. And then we have, finally, and now I think I'm going to pull up a different sheet of paper. I'm running out of room. Finally, we have, what if we're rolling 2 dice? Then, okay, so 2 dice. And we want A, the probability that the sum of the pips is 2. B is the probability that sum is 7. And C is the probability that the sum is greater than 9. Okay, well, here, since we're rolling 2 dice, what we want to do is we want to enumerate all of the possible outcomes that can occur. And so 1 dice could have possible outcomes. I'm going to call this die A. Has possible outcomes 1, 2, 3, 4, 5, or 6. And the other die B, has possible outcomes. I'll number these down here. 1, 2, 3, 4, 5, and 6. Since we're rolling both dice, then there are 36 possible, equally likely outcomes. A could be a 1 and B could be a 1. That's one possible outcome. A could be a 2 and B could be a 4. That's another possible outcome. A could be a 6 and B could be a 3. That's another possible outcome. So there are 36 equally likely or maybe I should say equally probable outcomes. So the probability of any particular outcome is going to be 1 out of 36. All right. Now, so what is the probability that we get a sum of 2? Let me we'll call that our red event. So what is the probability of the event that the sum of the pips is 2? Well, we can fill in this table here with the sums of all of the pips here, and then we can count the number of outcomes where the sum is 2. But I'm hoping that it's obvious that the only case where this is going to be true is if A is 1 and B is 1, then the sum is going to be 2. Okay? And because there's only one possible outcome from 36 equally probable outcomes of getting a sum of 2, then the probability is 1 out of 36. All right, now let's look at B here. The probability that the sum is 7. Well, here, again, we could fill in the whole table and identify the outcomes where the sum is 7, but we can do that a little more easily, I think. If A is a 1, then B has to be a 6 in order for the sum to be a 7. If A is a 2, B has to be a 5. If A is a 3, B has to be a 4. If A is a 4, B has to be a 3. 5 and 2. 6 and 1. Okay, and that's it. So these occurrences of the sum being 7, there are 6 possible outcomes that satisfy that event description. And because each of the outcomes is equally likely to occur, this probability is therefore 6 out of 36, or 1 out of 6, that we roll a 7. Okay, and then for the final one here, part C, we're looking for the probability that we get a sum greater than 9. Well, here again, we can sort of just work this out visually. 12 is greater than 9, 6 and 6. 11 is greater than 9, 5 and 6. And we can get that either by A being 6 and B being 5, or by A being 5 and B being 6. And then we have 4 plus 6 is a 10, 5 plus 5 is a 10, 6 plus 4 is a 10. So we have 10s here, these 3 outcomes. And I hope it's clear that that's it. All of the other sums in here are going to be less than or equal to 9. So it turns out that the probability that our sum is greater than 9 is also 6 outcomes out of a possible 36. And so that's also going to be equal to 1 out of 6. Okay, so that is our very basic introduction to simple probability calculations. We can think of the probability either as an average over an arbitrary number of trials, or as a proportion of some population. An outcome is just one particular outcome of some test or experiment or trial. An event is some set of possible outcomes. Alrighty.